Hi, I'm Celso Hirata, a professor of distributed systems at the Computer Science Department of Instituto Tecnológico de Aeronáutica. This video is about a chapter of my course, Distributed Programming. Distributed Programming is an advanced undergraduate course, and it also is a graduate course in informatics. I'm going to talk about the second class of distributed transactions. The distributed transactions chapter is divided into four main topics: introduction and recovery in centralized systems. That is the focus of this talk. The third one is supporting atomicity of distributed transactions. That's the core of this chapter. And also the topic about concurrency control for distributed transactions. This topic is very important to understand how transactions are correctly processed. So let's start with this topic, recovery in centralized systems. Recovery is made by using some mechanisms that are required in terms of operations in a distributed transaction. So before you proceed to recover, you have to understand what kind of recovery you need to provide. And that depends on the model of failure types in centralized database. Basically, there are three types of failure. Failure of loss of without loss of information. That happens when you have an exception, when you have a division by zero, for instance. Another kind of failure is failure with loss of volatile storage. That happens when you lose your memory. Sometimes you will have a power outage, so you lose what you're doing in your computer. But I mean, you don't lose any other information. For instance, information that is storage in disk. The third one is the most critical, is the failure with loss of non-volatile storage or permanent information. So in this case, you have failure of media. For instance, the disk head somehow crashes, so you lose all the information that you have storage. The failure of the last one, the third one, the loss of non-volatile storage, as I said, is the most critical. But the probability of this failure can be reduced by implemented replication or stable storage. Replication is not that easy, because you have to do that consistently in order to keep a coherence between many replicas. In that case, the more, if you have a lot of replication copies, so you're more, I would say, reliable. But the problem is you have to keep a management system to do this kind of replication. Okay, and the basic mechanisms to deal with failure or is to recover from failure is using log files. Log files are very basic, simple mechanisms. The intent of the log file is to try to undo or redo actions, operations that were performed by transactions. Usually, when you do actions, when the transaction is in the beginning, so you haven't done many things yet, so you want to abort the transaction. So you undo the operation that you have made so far. When the transaction is, I would say, well processed, is almost, for instance, finishing. So what you require to do is to most likely is to redo the operations, because you haven't completed all the operations. You want to be sure. So there's no, I would say, way back decision. So you have just to complete. So in this case, you have to redo the operations. One very important property of these operations that you have to see if these operations are independent. What is independency? Independency is when you perform this operation many times. For instance, in this case, I undo this action, I undo again this action, undo again this action. The result is the same, or just one application of this operation, undo. So you can have the application of many times, but the result will be the equivalent to performance than once. Okay? Why you need independency? Because the recovery procedure itself can fail. So it can be restarted several times. So if you have this property, I mean, you don't have to worry how many times you have done this redo or undo operation. So independence is relevant because it also helps us in the sense that he lives from the responsibility of knowing whether a certain action of undo or redo was already performed. If we apply that action as several times. So the idea is that it is no harm. You can, if you're not sure, you can apply once more. So the result will be correct. In the log record, you usually record, as I would say, some basic information. One is the identifier of the transaction. In general, the transactions includes many log records. So in the log file, for each record, you have to provide the ID of the transaction. The other one is the identifier of the record, because you have to correlate these records to other records that are part of the transaction. You also have the type of action with respect to that record. For instance, if you are registering a new customer, you have to insert the personal information record. So in this case, you have to insert if this customer has, for instance, some reason closed his account. Most likely you can perhaps delete his record. Or if this customer has modified his home address, so you can modify one of the fields of his information. So you also have to record, or to have in this log, the value that you are changing. So if, for instance, if you are changing the address, you have to know what is the old value, and the other information that you have to have is the new value. So you can keep track of the change that you are doing. Usually you will also have some additional information that links, for instance, all the records for that specific transaction. Let's see an example of log record. Suppose you have a transfer of $100 from account A to account B. Initially, account A is 1,000 and account B is 800. So the possible entries for the log file are, you can have 21, that's the IG of the transaction. That's you say that the transaction is beginning. So you can keep track when the transactions begin and when the transactions commits or finishes. So you also have the transaction 1 is modifying the record A. The old value is 1,000 and the new value is 900. In this, the third record, you have the ID as well of the transaction. Then you have the record B is being modified from 800 to 900. So finally, you have the last record. That is where you state that the transaction is concluded. And when you use log records, you have to have a choice when you should store the log record. Before the update in the database or after the database update. So the procedure is to record the log records before doing the update in the database. For that, you use the so-called the protocol log write ahead. Okay. The log write ahead protocol has two rules. One is before performing a database update, at least the undo portion of the corresponding log record must have been already recorded on a stable storage. Because since the database update can fail, so if you don't record, you don't store this information, you're gonna lose this information. Before committing a transaction, all log records of the transaction must have been recorded on a stable storage. That help us to redo the operations. For instance, if you have recorded all the records, when, for instance, if you have a problem in the transactions in the database transaction, you will know that you have the basic information to commit or to redo the updates in the database. So that's why it's wise to do that, to record all records that are required for the transactions in the log file. Okay, let's see how you recover the transactions. You have to be aware that you have many transactions being performed when, for instance, a failure happens. When a failure with loss of volatile storage occurs, so you have to go into a log file and perform certain operations. First, you have to determine or identify all transactions that were not committed yet when the failure occurred. You also have to determine that all the transactions that have committed. So have to determine transactions, not committed transactions, and committed transactions. And after that, you have just to undo the operations of the transactions that were not committed. And you have to redo the transactions that, the operations of the transactions that were committed. And undo the operations means that you are aborting or giving up the transactions. So that's why, I mean, it's easy to understand. Well, the question is why you have to do the transactions that were committed. Because you have to be aware that when you commit the transactions, you know that transactions is committed just in the log files, but you are not sure that transactions is committed in the database. So that's why you have to redo all the operations that were committed. Okay, and you have to do that, just recovery procedures for all the transactions that are in log file. So the problem with this approach is that the log files is generally huge file, I mean big file, because you contain hundreds of thousands, may contain hundreds of thousands of log records. So there is a way in order to, I would say, optimize this recovery procedure. The idea is to use specific records called checkpoints. What's checkpoints? Checkpoints are records that identify the current and non-completed transactions. Okay, so from time to time, for instance, 10 minutes, you have a record that in the log file that tells what are the transactions that are not completed at that point. So you use those records in order to optimize the recovery. In the sense that you avoid the total recovery. So the recovery procedure using checkpoints requires the following operations. You have to write on the stable storage all log records and all database updates which are still in volatile storage. The other one is to write to stable storage a checkpoint record. A checkpoint record is a set of active transactions that have not been committed or aborted. Using checkpoints, the steps 1 and 2 of the recovery procedure are changed in the following. First, you have to find the last checkpoint record. Then, the step 2 is to have to put all transactions written in the checkpoint record into undo set. In step 2, you have to put all the transactions written in the checkpoint record into undo set. So you're going to have two sets. One is undo set. You're going to have uncompleted transactions. You also have the other set is called redo set, that you have all the transactions that were committed. So the undo set, you have the transactions that were in the last checkpoint record, and the redo set is initially empty. So you read the log file starting from the last checkpoint record until its end. Then you have two possibilities. If you have a begin transaction record is found, you have to add this transaction into undo set. That's a new transaction, so you have most likely to undo these transactions when the failure happened. If a commit record is found, so you have to move the transaction from the undo set to redo set. So the transaction is already committed, but you're not sure if all the updates were made in the database. So that's why you have to redo those operations. I'll show you the recovery procedure using checkpoints, using an example. suppose that you have a checkpoint record that is recorded from 10 to 10 minutes. Okay, you start the recording at 24 hours or 0 hour. Suppose that the system collapses at 11 o'clock in 9 minutes. So the log file might have the following content. You can have at 11 o'clock, you have 3 transactions, T5, T8, and T10, that were activated at 11 o'clock. At 11 o'clock and 1 minute, you have, for instance, new transactions, transaction 12 that started. So transaction 12 is, transaction 12 is activated. 11:02, transaction 8, that is one of the active transactions, has modified the record A from 1000 to 900. At 11:03, transaction 10 committed. So in this case, transaction 10 completed. Okay, so you have to record that information. 11:04, you have the beginning of new transaction, a transaction 13. At 11:05, transaction 13 modifies the record G from 5,000 to 200. At 11:06, transaction 13 commits. Transaction 13 completes. 11:07, transaction 12 modifies the record C, the value from 110 to 145. So when you use the procedure to recover using those checkpoints record, you're gonna start the processing from the last checkpoint record. So in this case, it's 11 o'clock. You're gonna see that you have 3 transactions. So you're gonna put these 3 transactions, T5, T8, and T10, in the undo set. The redo set is empty. When you find a new begin transaction, you add this transaction into undo set. When we commit a transaction, for instance, in this case, transaction 10, you remove the transaction from this set, undo set, to redo set. So in this case, you are moving the transaction 10 from the undo set to redo set. In this case, you have the beginning of a new transaction. Transaction 13 is inserted. Transaction 13 in 11:06 completes, so you have to move the transaction 13 to redo set. So at the end, you have to undo all the operations related to those transactions, T5 to T8 and T12. You have to redo all the operations that are related to those transactions, T10 and T13. Okay, so the recovery procedure using checkpoints is somehow optimized, and so when you use checkpoints, because you do not have to go through all the records of the log file. Okay, and so far we have considered only the recovery from failures without loss of stable storage. Okay, you have just considered the loss of volatile memory or volatile storage. There are some recovery techniques that were developed as well for loss of stable storage. Okay, it's very important to distinguish 2 possibilities when talking about stable storage. A failure in which database information is lost but logs are saved, and failures in which log information is lost. In the first case, the recovery technique consists just of redoing all the redo of all committed transactions using the log. The redo is performed after having reset the database to a dump. Okay. In the second case, it's impossible to restore the database updates because you've lost the log files. So in this case, it's catastrophic. So you should assure that that situation never happens. Okay, and that's finishes your topic, recovery in centralized systems. So in the next topic, you're gonna see how the protocol, two-phase commit protocol. The idea is to ensure the atomicity property in distributed transactions.